Now that we've created a density source, let's do our initial simulation setup. So let's start by creating a DOPNet. I'll call that DOPNet dust and make sure the start frame is set to 985 and then dive inside. And we'll be running this sim with the Pyro solver. And you could run this with the smoke solver as well. The Pyro solver is essentially a wrapper around the smoke solver. If you dive inside the Pyro solver, you'll see that internally it's just using a smoke solver here. It just has a lot of extra features already set up and plugged in. So we're going to use that for convenience, and we need an object for this to process. So let's create a smoke object and connect that to the first input of that Pyro solver. Now we need to set an initial size and center position for this smoke object, and I like to base this on the first input of the DOPNet. So I've set up a preset on my smoke object here that sets an initial smoke box based on the size and centroid of the first input. So then outside of this DOPNet, we need to connect an initial sim bounds. So we can get that initial bounds from our original source geometry that we're using here. And instead of connecting that to the unpacked geometry, let's connect this up to the transform pieces without doing this extra trail computation. So I'll bump this over to the side just to make this a little bit more visually clear, like so. And I'm going to time freeze this so that our initial bounding box doesn't keep changing. So I'll drop in a time shift and we'll break that expression and set that to the start frame 985. And then we'll add a bounding box to this with our bound SOP. And then we can give this a little bit of padding on that initial shape. It looks like a few units will be plenty of padding for us. You can remove it from some of the areas you don't need if you'd like. For example, I don't think we'll really need that padding on the lower Y dimension, so I'll remove that. And I'll drop in a null and call this initial size. And now our smoke object initialization will be based on this input size here. So if we rewind to our start frame and dive back inside, you can see we have our smoke object initialized, and we can start adding our density source to this. So let's drop in a volume source, and we can connect that to the last input of our Pyro solver. If you hover over that, you can see in the tip text here that that's our sourcing input. So you can connect that to our volume source. I'll call this volume source primary because we're going to be adding a whole bunch of volume source nodes in here. Now in this initialize parameter, if you just click on source smoke, it's not actually going to change anything because it's already set to that. But if you flip this to a different initialization type and then back to source smoke, then this will be set up to source into the fields that we need for our sim. So that will create a density field, and this will pull the density field from SOPs and insert that into our DOP field. And this also looks for a temperature field from our input as well. And we haven't created a temperature field, but we can just use the density data for the temperature in the sim. So for the source volume, if we just set this to density, then the same density values here will be used for the temperature information inside the DOPNet. And as I mentioned, when we set up our density source, we're going to be setting up our velocity influence separately, so you can just get rid of this V influence here. And so we have our DOP field targets set up, but we haven't actually pointed this volume source to our density source in SOPs, so we can just point this to /source density. Now if we rewind the sim and start stepping through the frames, then you'll see we have our density being sourced based on our emission that we set up in SOPs. Now this sim is currently pretty low resolution. Our source in SOPs should be high enough resolution for our sim, but in the DOPNet, this smoke object is set to be a bit too low. This division size of 0.2 is a bit large for our final quality. We'll have to make this a much smaller division size for the final sim. But for our initial setups, we can keep this pretty low res just to see that everything is working properly. Now in our initial setup, we can also add some calling based on the camera frustum so that areas outside of the camera view are removed. And we've already set up a volume for our camera and SOPs here, so we can just use this data as a multiplier in our simulation to cut out any of the density data that's not within here. So in our DOPNet, we can just create another source just like we did for our density. We can just copy our existing volume source and we'll merge those together. And I will call this volume source camera. And for the camera, we're just going to use this for the density so we can get rid of the temperature here. And then for the SOP path, we can point this to ... / volume from camera. Now at the moment, you can see this just adding the density from our camera volume, but that's not very helpful. Instead of adding this density, we want to set this operation to multiply. So when we set that to multiply, we're going to be preserving all of those density values within the camera frustum, because everywhere within that view is going to have a density value of 1, and everywhere outside of this camera view will have a density value of 0. So when that's multiplied in with our simulation density, that's essentially just setting everything outside of view to a value of 0, and then our simulation resize can shrink so that we're not wasting that computation area. Now we haven't set up that resize yet, which will optimize our box and remove the areas that don't have any density data and that don't need to be computed. But before we set up that resize, let's see what this looks like with that camera frustum calling applied. Now if we play back a flipbook of our simulation, you can see that the frustum calling is not working because we missed one very important step. These volume sources have a clamped to active region option here, and with that turned on, that will prevent our volume source from returning 0 values outside of the input volume. And in order for this frustum calling to work, we want those 0 values outside of that volume region, so you can turn that clamp to active region option off, and then we'll do a new flipbook. Now reviewing our new flipbook, it looks like the camera frustum calling is working correctly. You can see those density values being wiped away as the camera pans away. And right now we're still simulating this entire smoke object box because we haven't applied a resize to this. So let's add a gas resize fluid dynamic, and we can wire that into the second input of our pyro solver that goes in the pre-solve there. And this is automatically set up to check the density field for empty areas that we don't need to simulate. So if we start stepping through the sim, you'll see that our smoke object box immediately disappears because we don't have any density data on the first frame. So the solver says, we have nothing here, we don't need to preserve any of this area. Now one way to fix this problem is to delay the resize by a frame or two. So on this delay frames parameter here, I'll set that to 2. So for a given region of our smoke object box, it will wait until that's been empty for 2 frames before it resizes that area away. So now when we step through the sim, you can see this is waiting a couple frames before it starts to resize this. And now that we have density data in there, that resize can safely remove those empty areas. Now right now we have very little padding between the density data and the edges of our smoke object box. And this can be pretty dangerous because if we have emission areas and SOPs that are outside of the box, then we might have nothing emitted in the sim since it's outside of the simulation area. Now one thing that can help to avoid that is to increase the padding. So if I turn that up to 2 instead of the default of 0.3, you can see that gives us a little extra buffer around our sim. And you also have per axis padding scales here. In this case, I don't think we really need it, but if you were to emit some smoke from an object that was moving pretty fast in X, then perhaps you would want to greatly increase the padding in the upper X dimension just to give a whole lot of extra buffer in the fast moving direction of your object. But in our case, we can just do a uniform padding here. Another thing that can be helpful that we don't need for our sim is to use a tracking object, and this will force the smoke object box to include whatever the bounds of this tracking object are. So if you had an emission object in SOPs and you wire that into this area here, then this simulation box will always include that object. But in our case, the area is pretty stable, so we don't need that. But we do have to watch out for this field cutoff. Sometimes this default field cutoff is okay, but in cases where you see the low density areas of a simulation starting to suddenly disappear, then that could likely be caused by this field cutoff area. What this means is that a density value of below 0.005 is going to be removed from the sim. And sometimes that's fine because a density so low could be practically invisible anyway, but sometimes you really do notice those fine densities being removed, especially if you're taking your simulation data and making it much more dense at render time. So sometimes it's a bit safer to lower this field cutoff to something like 0.002. And before we run a new flipbook of our sim, let's tweak a couple other things. If you look back at our previous flipbook, you can see that all of our dust is rising in the air like smoke, which is not correct behavior for dust. Our dust is really just a cloud of heavy particles that should be slowly falling down and settling instead of rising upwards. Now this rising motion is controlled by the buoyancy settings, and the buoyancy is driven by the temperature. So you have a couple options here. You could use some negative buoyancy on the pyro solver. We can flip this buoyancy direction to -1. And this is why I added temperature to my simulation based on that density data and the volume source. Because this buoyancy is driven by temperature, and higher temperature values will rise more quickly. So you need to have this temperature field in order for buoyancy to work at all. However, in my version of this shot, I just set the buoyancy to 0, and instead I used some gravity force. So you can just drop in a normal gravity DOP node, and in my case, I turned this down a bit. I used a multiplier of 0.4 on that default gravity so that this stuff doesn't fall too quickly. And before we run a flipbook of this version of the sim, let's fix our display a little bit. Sometimes you have some artificial clamping in your viewport of the volume quality, so you can open up your display settings, and under the texture tab, you can turn off this limit resolution checkbox for 3D textures. We also have some controls for the volume quality in SOPs, but first we'll need to import that data from the DOPNet. We can't view it just by displaying the DOPNet itself. So you can create a DOP import fields and drag and drop your DOPNet dust into the DOP network there. And for the default object, we'll just type in the name of our smoke object, so that'll be smoke object 1. And under presets, we can select the smoke, but we're not going to be using rest data for this, and we don't need to export the temperature or the color. We're only interested in the density and the velocity. So if you display that DOP import field, you can see we're pulling in that information from our DOPNet, and sometimes we can improve the display of this with the volume visualization SOP. So if you drop that in and connect the DOP import field to that, and then we'll select the density field from the drop down here, then we can turn on this max vis res option. Now in this case, our volume is pretty low res, so if we start turning this up pretty high, we probably won't see much difference. So if we turn this up to 1024, this can't really add quality that's not already there, so it doesn't look any different than if we have this turned off. But you can certainly see the difference if you start clamping this volume quality lower. Like if we turn it down to 64, you can see this is forcing the display to a pretty low res version. So when we are running higher quality sims, we can potentially improve the viewport display by turning this up, typically to a value of about 1024. And volumes tend to look very blown out in the viewport with Houdini's default headlight, so we can add a custom light that we use just to view our volumes a little bit better. So I'm going to jump out of our dust setup here. Actually, before I do that, I'm going to pin the viewport inside the dust setup and then jump out. And I'm going to make sure that my current redshift light in this scene is not enabled in the viewport. And then I'm going to create a normal Houdini light. And I'll set that light type to sun. And now if we turn on the lighting in the viewport, you can see we're getting some shadowing on our volume, and this sort of detail makes it much easier to see what's actually happening in the simulation. Now we're getting some very dark shadowing on the far side of this, so you may want to tweak the light rotation to an angle that works a bit better for the camera view. In this case, I'm finding a value of about 80 or so seems to work pretty well. If you already have a light direction established in your scene, you can base it on that. Otherwise, you can just base it on an angle that looks good from your render camera. Now once we flipbook this with the updates, you can see that all of our dust is falling a bit more realistically now that we've gotten rid of that upwards buoyancy. We have that camera frustum calling working correctly. And right now the dust is pretty light and low res and not very detailed, but that light that we added is helping us to view this much more nicely than the default Houdini headlight would.